Hey everyone, we're going to start chapter 9, our last chapter. Congrats on getting to this point in Orgo 1. We're finally wrapping up, and in this last chapter, we'll be talking about the functional group alkynes, which are triple bonds. Like the past, we'll first dive into properties of alkynes and also how to name them, so the nomenclature. And then we'll move into the reactions of triple bonds. First, let's talk about where alkynes come from. They are kind of an interesting bond. We don't see triple bonds that often, though they are present both synthetically and biologically. We see them naturally. They, again, as a reminder, are a carbon-carbon triple bond. That's the definition of an alkyne. We've talked about them in the past when we brought up hydrocarbons way back in introduction of hydrocarbons. I talked about the differences in alkanes, alkenes, and alkynes. One of the other special types of alkynes that we'll be talking about is when the triple bond is at the end of a chain. We call this a terminal alkyne. So this would be an example like this. Here we have a three-membered hydrocarbon. And this triple bond is at the end of a chain. And notice that it has this one hydrogen attached to the last carbon in the triple bond. This hydrogen is important. We'll be talking about it later because it has a unique acidity to it. It's kind of this lone hydrogen sticking off the end of a triple bond. Now, any alkyne that is within a chain, so if we were to continue this chain with more carbons, for example, is called an internal triple bond or alkyne. Alkynes can be produced. So for example, acetylene, if you're familiar with acetylene, it's actually also called ethyne. It's a carbon-carbon triple bond, the most simple hydrocarbon with a triple bond. This can be produced in a reaction using calcium carbide, which is an ion form of calcium and this triple bond carbide ion with water. It can also be produced through a dehydration reaction. Well, we've talked about these reactions when looking at double bonds, but you can also take a double bond and further dehydrate it with heat to make a triple bond. There's also numerous examples of natural alkynes. For example, many fatty acids have this triple bond, such as steroic acid, which includes a triple bond in it, and taururic acid. There's also other natural products that contain alkynes. For example, many antibiotics have them. This one in particular is interesting because it has triple bonds within a ring system. There's this really interesting ring upon rings. We've actually talked about this situation where you have multiple rings bisecting each other, but this one has triple bonds included in the ring. And actually, I'll bring up, interestingly, I think on the first lab, the lab worksheet, many of you included a interesting triple bond product. You were asked on one of the questions to include an 18-membered ring. And a lot of people, and this is what I was expecting, drew out a simple single bonded ring of 18 carbons. So it was just, a bunch of single bonded carbons, 18 of them in a ring connected. But a few of you included a product that is a real product, although it is a synthetic product in which It is an 18-membered ring, but it instead has alternating triple bonds. Triple bonds and single bonds. It goes all the way around. There's 18 carbons. Alkynes also have been found in other places like other planets. This isn't that surprising because it's around extreme pressure and heat in which these triple bonds are more likely to form. Okay, well, let's dive into the nomenclature on how to name these triple bonds in combination with all of the other nomenclature that we have gone through. So like our double bonds, when you are deciding the longest chain, you want to include the triple bond in the parent chain. Now, if it is alone, it's the only functional group there, you're going to replace that ane with an yne. We talked about this again before in our early chapter when talking about hydrocarbons. Alkane is for single bonds. Alkyne is used when there are one or more double bonds, and alkyne is when there are one or more triple bonds. And we'll talk about what to do when you have multiple double bonds and triple bonds combined. You also want to number the parent chain in a way that the first multiple bond, that's a double bond or a triple bond, has the lowest number possible. Now, if you have a tie between a double bond and a triple bond, you have to decide which one gets the lower number. The double bond is given priority. So here's an example at the bottom with our 5 carbon long chain. You can see it has 5 carbons. Don't be fooled by this triple bond. It looks a little odd ending almost into nothing, but there is a carbon, of course, at the other side of that triple bond. So don't forget to include it in counting. So 5 carbons, it's a pent. And if we were to start numbering on this end, our double bond would get the 1. And if we were to start numbering on this end, our triple bond would get the 1 position. So our double bond will get priority in this case, which is why we get 1 ene. Remember, ene is for double bond. 4 yne. Yne is for triple bond. Now, what if you have a triple bond on a substituent group? This is on a side group. You can have triple bonds on a side group, and we'll see examples of that. It gets this really interesting ending. It uses the yne to represent that it is a triple bond, and the ul to represent that it is a side substituent. Remember, when we have groups that are substituents in the past, we've seen like meth, ul. The ul represents that it is a substituent. So it's going to get this yne ul. Now again, on this topic of priority, as I said, when you're deciding between alkenes and alkynes, the numbering of the alkene will get priority if there is a tie. So for example, here is this molecule. Now, starting numbering at this end with the triple bond gives the triple bond the number 1 and the double bond the number 3. If I were to number at the other end, for example, here, 1, 2, 3, the double bond still gets a 3, but the triple bond would get a number 5. So we still are going to number on this end. Remember, you always want to choose the side that gives the multiple bonds lowest numbers in general. Only when there is a tie do you have to give the double bond priority. Now, even though the double bonds get priority in ties for numbering. They are named in an arrangement that is alphabetical. So notice that the name here is pent 3 een and then ein. Now, this is the only case where you see this. We're going to look at cases where you have other types of substituents, for example, alcohols, and alcohols would be at the very end. This end position is usually given to the priority group. But in the case of a double bond and a triple bond, een comes before ein, even though een usually gets the lower number. So in this example here, this is where we had a tie, and the 1 position was given to the double bond, and the 4 position was given to the triple bond, but it's still named in an alphabetical fashion, pent 1 een, 4 ein. Now, if you want to look at more about priority and which group gets priority, in a whole list of all the functional groups, you can click on the link that I've attached here. This shows every functional group, ones that we have not gone over even, but you will go over in organic too, and where they are as far as priority in naming. So we've just covered basically the double bonds, triple bonds, and alcohols and halides, and of course side chains like alkanes, alkyl groups. But if you want a more expanded list and to try to start understanding where things are in naming based on their priority, definitely click on this link here to kind of explore into that more. Okay, let's do some practice to kind of get a hang of how we name these complex molecules using the nomenclature rules we've seen so far. I'm going to give you some hard examples so we can practice kind of combining everything that you would see. So let's start, this is an easier example. Let's start with this small molecule. First, let's find the longest chain. So I want to include all of the bonds, the multiple bonds, and our alcohol should be attached in our longest chain. And in this one, it's easy. If we just do this straight chain, we include everything. Remember, there is a carbon here. 1, 2, 3, 4, 5. So our longest chain is a pent. I'm not going to put the ending stuff because we're going to decide that based on our chains, our groups here. So what else do we have on this chain? There is an alcohol, there's a double bond, and there's a triple bond. So that means that there is an all group, an ene group, and an ein group. And I'm going to decide where they go and their numbering. First, let's decide the numbering of the chain. Here's an instance where, depending on which side we number, we're either going to give priority to the double bond or the triple bond. OH and alcohols generally get priority over both of these, but it doesn't matter which side we start from, the OH is always going to get the number 3. So here, if we start on this end, we give priority to the double bond, and if we start on this end, we give priority to the triple bond. As I just said before, double bond wins in this contest. So we'll start from this side. 1, 2, 3, 4, 5. That means our alcohol is on position 3. Our double bond is on position 1. And our triple bond is on position 4. Now let's rearrange these in the ending of our molecule. Here, remember I said that when talking about double bonds and multiple bonds, the ene comes before the yne. So this should be pent, 1 ene, 4 yne, and the alcohol part always comes last. It gets the most priority, 3 all. This is how you would name this molecule. Again, the group in our naming here that comes at the end, as far as what we've talked about in functional groups, will always be the alcohol group, if it is there, as far as the naming. And then when we're looking at double bonds and triple bonds, the double bond comes before the triple bond. Okay, let's try another example. Again, this is a harder example. First, let's decide what our base hydrocarbon is and how big it is. Here we have a ring as our base. It's a 6-membered ring, and there are no double bonds or triple bonds in it. And there's no other functional groups that get priority like alcohols attached to it. So this is a simple base of a cyclohexane. Now, let's look at the substituents on the cyclohexane attached to it. So far, we have this iodine group, which gets the iodo name. We have a methyl group. This group right here is one of those special groups I mentioned at the beginning and told you to memorize. It is a isopropyl group. And this is a case where we have a triple bond as a substituent. This is a triple bond made of 2 carbons. So it gets eth for 2 carbons. And remember, its ending here is going to be ethene ol. Okay. Now let's number these groups based on the priority that they have. Here we have side groups and a triple bond and a halide. In this case, our halide is the attachment that has the highest priority as far as numbering comes. We don't have any alcohols present, so there's no other priority except to the halide. And we're going to number in a fashion starting here to give our next set of higher priorities to the available side groups. So this side group with the triple bond gets a higher priority than this side group substituent that is just single bonds. So we will number in the direction around the ring this way. So based on our numbering, our iodo is at position 1. Our methyl group is also at position 1. Our isopropyl is at position 5. And our ethenol is is at position 3. Now there's one more thing here. If you've noticed, there is a chiral center that has been denoted at this carbon. So now let's decide the stereochemistry of this carbon, and then we'll put all the pieces together for the end of the name. So when looking at this carbon, we first want to decide what the lowest priority group is. Notice that there's no hydrogen here. Usually hydrogen is our lowest priority group. And I say put it in the back and ignore it. But we don't have a hydrogen attachment. In this case, our lowest priority group is this methyl group. If we were to check our iodine versus this CH2 versus this CH2, the CH3 has the lowest priority. And so we will treat it like a hydrogen, meaning we want it hashed in the back, which it is, and we want to ignore it when numbering. This is a case you could get. Usually I give you hydrogens, but be wary that you could have another group be your lowest priority group and the group that you will ignore. Okay, now let's number based on what is left. Remember, we're looking at highest atomic number. And in this case, iodine definitely gets the first priority when compared to the other two groups. This is a carbon and this is a carbon. So our iodine will get 1. Now these carbons that are left are identical, and these carbons here are identical. So we have to continue to looking at the first point of difference, which would be here and here. And let's look at which group here is going to get higher priority. So this carbon is in a triple bond, and we will say that that carbon is thus attached to 3 carbons. This carbon is attached here and here to a carbon and a carbon, and not shown, hidden, is a hydrogen. So in this case, the triple bond gets priority. So again, when numbering our priority groups, we would go here and then here. When we connect those in rotation, you can see that this is a clockwise rotation, which means that it is an R rotation. And the position of the chiral carbon is on position 1. So this is 1R. Here's all the pieces we have. Now let's fit them together in naming the final compound. So of all of the pieces, remember that we are going to be writing them in alphabetical order. In this case, our ethynyl will go in the front. So 3-ethynyl. And then the next one, in this case, is going to be the I group. And when looking between iodo and the isopropyl, remember that this iso actually isn't counted. So the P is what counts. So it would be 1-ido. And then next would be the isopropyl. And then 1-methyl cyclohexane. And in front of all of this, we always put the stereochemistry at the very front in parentheses. This would be 1R. 1R, 3-ethynyl, 1-ido, 5-isopropyl, 1-methyl cyclohexane. Okay, let's try another one. This is another ring group. Here we have, again, multiple types of groups present. Double bonds, triple bonds. We have a double bond in a ring. And we have a stereo center again. So let's look at naming this one. Our base here is a 6-membered ring. So again, it is a cyclohex. Now let's see what's attached to this. There is a double bond directly in the ring. So we know that there will be an ene portion, and it has an alcohol attached to it. So there will be an all portion as well. What else is there? There's this substituent group. It is a side group of a triple bond that is again made of 2 carbons. So this is that same one we saw. It's an ethyne for the triple bond, ol for a substituent side group. Okay, let's do our numbering now. In this case, remember that the alcohol will get priority. So we're going to start numbering here at the alcohol, and then continue numbering in a way that gives double bonds in the main, or multiple bonds in the main chain, the highest priority possible. So you actually would number this way because we want to give the double bond that's in the main chain the highest priority. So it would go this way. Okay, so that means that our all is at 1. Our double bond, the ene, is at position 3. And our substituent group, the ethynyl, is at position 6. Now what's left? Again, there is a carbon here that has shown chirality and stereochemistry. So we need to determine its rotation. Here we do have a hydrogen as our lowest priority group, and it is already in the back, so we can ignore it. And then assign priority around, and then we will determine RS. So here, this carbon is attached to a carbon here, and an oxygen. So oxygen has the highest atomic number. It will get priority 1. This carbon and this carbon are the same, but let's look at what they are attached to now. This carbon is attached to 2 hydrogens and a carbon. This carbon is attached to a carbon here, a carbon here, and it also has a hydrogen. So this is the first point of difference, and this carbon will get higher priority. Our numbering then would be, this would be 2, and this would be 3. We rotate this way, and this is a clockwise rotation, which means that it is R. And the chiral carbon is on position 1, so it's going to be 1R. Okay, let's put it all together then. Put our stereochemistry in the front, 1R. Now, we have only one substituent that goes in front of all of this. The other things that are part of the ring go in this portion of the name. So our 6-ethinyl, that is a side group substituent. And then we have a cyclohex 3-ene-1-ol. So notice again, the double bond name, because it's in the ring, goes within the cyclohex naming portion. And alcohols, if alcohols are present on the main chain, they also get this priority of being within the name. Okay, let's try one more practice. Here we have to decide first where our longest chain is. So we could count from here, 1, 2, 3, 4, 5, 6. We could also count this way, 1, 2, 3, 4, 5, 6, 7. And the last version we could count is this way. 1, 2, 3, 4, 5, 6. Now you saw which one actually has the most number of carbons, the longest chain, but remember that our parent chain should always try to include in priority the alcohol, and secondly, any type of multiple bonds, so double bonds or triple bonds. So the longest chain that also includes these in the parent chain would be this chain right here. This is what we will name as our parent chain then. So this is a 6-membered chain, hex. It has an alcohol in it, so there's an ol there, and it has a triple bond in it. There's an -ine there. And there are no other groups except for this side group. This is now a side chain, and it is 3 carbons long, so it is a pro-pull group. Now let's do our numbering. Now remember that alcohols get priority over our multiple bonds, so we will want to give the numbering starting closer to the alcohol. which results in this numbering, meaning our alcohol is on position 2. Our triple bond then will be on position 4. And our propyl group is attached right here at position 3. Now let's combine everything in the name. We'll put any substituents in front, and then anything that is part of the main chain goes within the main name of the alkyl group. So this would be a 3-propyl hex 4-ine 2-ol. Remember, the alcohol always comes at the end. Okay. All right, well, that's it for naming practice. It's a lot of hard practices. Again, some of the best things you can do is just use your chem draw and make molecules and then see what their name is. Test yourself in naming them. Okay, on to physical properties of alkynes. General physical properties compared to alkanes and alkenes is very similar. They have low boiling points, low density, and they're not very soluble in water. They're very insoluble, actually, pretty hydrophobic. That's because they don't really have any polar functional groups. Their structure and bonding is an SP hybridization. And because of this triple bond and SP hybridization, it's actually a very short bond. We looked at this in our first lab, actually, when we looked at bond length. Triple bonds are the shortest bond and they are stronger compared to a double bond. The hydrogens attached to triple bonds and any other carbons attached to a carbon on a triple bond is also slightly shorter. So the triple bond kind of shrinks in and pulls other groups attached to it closer. Triple bonds are linear. They're naturally linear and flat, and again have this SP hybridization. Actually, when looking at the drawing, you'll notice most of the time when we draw single bonds, it's like this, or even in double bonds, we can distinguish which way they're facing, cis or trans, but we have some kind of up and down positioning. When you draw a triple bond, it's always drawn like this. So notice that the carbons don't go out like this in any direction, and that's to represent that this triple bond is linear and flat. It actually keeps everything in a near it planar. So one bond away from it, like this, can have some rotation and movement, but where the triple bond is flat and linear, and that's why it is drawn this way. And it can, again, look a little confusing. You have to remember that there's a carbon here and here, especially when it's on an end like this. So again, if you wanted to look at general comparisons of these alkynes to other hydrocarbons, they're pretty similar. Single bonds sp2 and those triple bonds sp. Now let's look at the actual hydrogens on these bonds. PKA refers to PKA when you have this triple bond present. Now, alkynes also can act as nucleophiles. The triple bond itself, I'm not talking about the hydrogen, but the triple bond itself can act as a nucleophile, just like a double bond. We just spent a lot of time talking about double bond reactions and how the double bond itself acts as a nucleophile. It donates electrons. It can open up and donate electrons to form bonds. So just like these double bonds, the alkynes have a nucleophilic area upon the triple bond, and thus they also can undergo this electrophilic addition. You have something electrophilic, this triple bond will donate its electrons, open up, and bond to an electrophile. We'll go into this more when we talk about reactions of the triple bonds themselves. Now going back to that trait of acidity, I mentioned that alkynes are relatively acidic compared to alkanes or alkenes, and that is because of that terminal hydrogen. So these terminal alkynes, remember those are the ones that are at the end of a chain, are pretty acidic. Remember that these triple bonds have a lot of S character. They're sp hybridized. That's 50% S character, 50% P character. And because of this high amount of S character, it means that the lone pairs are close to the nucleus on the carbon and pretty stable. And this hydrogen, thus, is actually can be pushed further away. It's polar. It's not necessarily pushed further away, but the electron density is pulled closer to the carbons, and so the hydrogen is left more polar and has a slightly positive amount of charge, making it a little bit more acidic. So even though alkynes are relatively acidic compared to alkenes and alkanes, they still aren't that acidic. Don't think that they're a very strong acid when looking at all of these other acids we've seen. Again, their pKa is 26. Remember that strong acids actually usually have a pKa of 1 or lower. Sometimes they'll have them in a decimal point, like 0.01 of a pKa. So they're not that strong of an acid, and water is not even strong enough to be a base when you look at a triple bond hydrogen. And neither is a decently strong base, which is a hydroxide ion. We usually see hydroxide ions acting as a pretty good base, but these aren't even strong enough to pull off that hydrogen on a triple bond. Now, amide ions are usually strong enough. They're usually the base of choice when trying to do a reaction in which we're using a terminal alkyne as an acid. Carbanions, so these are carbons in alkanes and alkenes that have a negative charge on them. These also can work well for acting with a terminal alkyne to pull off that hydrogen. But generally, amides are pretty strong bases. They're stronger compared to hydroxide or especially to water, and can act to pull this proton off of a terminal alkyne. So noting that and looking at this question, which of the following bases would be strong enough to completely deprotonate propyne. So propyne has a triple bond, right? Has that -ine ending. And we just said here that amide ions are strong enough as a base of choice to pull off that proton. We said that things like water or even hydroxide ions are not strong enough. So let's look first at our choices. A is an amine, an NH3. Notice this doesn't have a charge on it. This is a stable amine and not an amide ion. This is an ion of a amine. So it has a nitrogen and 2 hydrogens, but a negative charge. So it's an ion form of an amine. It's an amide ion. So this is just a normal amine. It's not that basic and is pretty stable. Here is an alcohol. Talked about alcohols, not at all strong enough for this type of deprotonation. Now here we have these 2 salts. Notice when you have something like sodium or potassium or calcium in front of something, that denotes that this is an ionic bond. That means that really this breaks up into this ion pair, and this breaks up into this ion pair. So again, remember when you see these metals bound up to organic molecules that they are an ionic bond. So this will form, D will form a hydroxide ion, which we also talked about is not strong enough. But C will form an amide ion, which is strong enough to deprotonate a triple bond. Okay, well that is it for nomenclature and our general properties of alkynes. Next, we're going to be talking about more of those reactions. We actually just hinted that triple bonds can also do electrophilic addition like double bonds, so you'll be seeing that, and some other types of reactions you'll see with triple bonds. Generally, these are going to mimic what reactions we've seen with double bonds, but have a slightly different end product than what you saw with a double bond.